The paper presents a critique of Zotter's equation for electron storage rings, specifically challenging its description of the scaling law of potential well bunch lengthening. An alternative, self-consistent equation is proposed to better describe this phenomenon. The authors explore the implications of this new equation in predicting bunch lengthening and extracting effective impedance from bunch length measurements. The paper begins by examining the motion of electrons in the longitudinal phase space, emphasizing the influence of the RF system and the deformation of the potential well by longitudinal wake fields. A cubic equation for bunch lengthening is then derived, representing a leading order perturbation from the longitudinal wake fields. This equation is employed to calculate the incoherent synchrotron frequency and the effective impedance, both of which are essential components in collective instability theories. The proposed equation offers a more accurate representation of the complex interplay between the RF system, wake fields, and the resulting bunch lengthening in electron storage rings. This refined understanding has significant implications for the design and operation of these devices, as well as the development of new theories to describe their behavior. In electron storage rings, the power density of the U1D45 mode is critically dependent on ring length and bunch length. The concept of effective impedance plays a pivotal role in understanding this relationship. Effective impedance, a measure of the ring's impedance as seen by the beam, is essential for accurately modeling and predicting the behavior of electron beams in storage rings. A crucial aspect of beam dynamics is potential well bunch lengthening, which is governed by a cubic equation derived through a series of mathematical manipulations. This includes the application of Fourier transforms to resolve the longitudinal impedance into its harmonic components and the solution of differential equations to account for the interaction between the beam and the ring. The cubic equation, a key result of this analysis, is sensitive to the accurate calculation of impedance, particularly the correct factor in the denominator. Notably, previous literature has been shown to contain errors in this regard, highlighting the importance of precise calculations in this context. These findings underscore the significance of rigorous impedance calculations in electron storage rings, with implications for the design and operation of these complex systems. The prediction of potential well bunch lengthening in electron storage rings relies on equation 22, a model consistent with the Heisinski equation and beam-based measurements. However, this consistency is conditional on the total longitudinal impedance of the ring being well approximated by a pure inductance and the potential well remaining well quadratic. Notably, small 3D discontinuities, such as obstacles or cavities, and small angle transitions, like collimators in colliders or tapers sandwiching small gap insertion devices in light sources, are important sources of inductive impedance. A self-consistent equation for bunch lengthening is derived from the Vlasov-Fokker-Planck equation, which governs the evolution of the circulating beam. Solving this equation yields the Heisinski equation, describing the stationary distribution of the bunch. The wake potential of the bunch is defined, and the synchrotron tune is introduced. The authors then derive an equation for potential well bunch lengthening, equation 31, a cubic equation in terms of the bunch length. This equation is formulated in terms of the impedance, and an expression for the effective impedance is provided, equation 33. However, the authors highlight the limitations of the cubic equation, noting that it may not apply well in certain cases, such as damping rings or future circular colliders, where the resistive part dominates the total impedance. The research paper discusses the Heisinski equation, an exact stationary solution of the Vlasov-Fokker-Planck equation, and its application to electron storage rings. It presents a new method for calculating the effective impedance, denoted as U1D44 def, barred BL, which is always real and not complex, indicating bunch lengthening. This method is derived from the Heisinski equation without any approximations, making it a self-consistent equation for potential well lengthening applicable to electron storage rings. The paper emphasizes that this equation is not valid at beam currents above the microwave instability threshold, where the beam energy spread will increase. The paper then formulates the center of mass and effective impedance using a Gaussian driving bunch with a length of 0.5 mm and sums to create the pseudo-green function wake. The corresponding impedance is calculated by Fourier transforming the wake data, showing a decay at high frequencies due to the chosen Gaussian window function. The beam parameters used to solve the Heisinski equation include beam energy, ring circumference, slip factor, bunch length at zero current, momentum spread, and synchrotron tune. The paper also presents numerically obtained Heisinski solutions with varying bunch populations, corresponding to different normalized currents. These solutions are shown in Figure 2, illustrating the lengthening of the bunch and the centroid displacement as a function of the normalized current. The Heisinski solution for super KEKB HER reveals the bunch centroid and RMS bunch length as a function of normalized current, showcasing a non-constant effective impedance. This contradicts Zotter's cubic equation, suggesting inductance-impedance dominance. In contrast, super KEKB LER exhibits a fairly constant effective impedance, indicating a pure inductance description is sufficient. The new Heisinski-derived equation is useful for comparing impedance calculations with beam-based measurements in electron storage rings. The authors acknowledge previous work on impedance modeling and single-bunch collective instability simulations, citing several studies that have laid the foundation for their research. They emphasize the importance of accurately modeling the electromagnetic interaction between the particle beam and its environment in order to simulate collective instabilities. The paper discusses various impedance models, including the resistive wall model, the geometric model, and the hybrid model, each with its own strengths and limitations. The authors highlight the need for a comprehensive understanding of these models to accurately simulate beam dynamics in high-energy particle accelerators. In terms of single-bunch collective instability simulations, the authors draw upon previous research that has demonstrated the importance of considering both transverse and longitudinal instabilities. They discuss various simulation techniques, such as the linear stability analysis and the particle-in-cell method, which are used to study the growth rates and characteristics of these instabilities. The authors also emphasize the role of wake fields in driving collective instabilities, particularly in the context of high-luminosity colliders where intense electromagnetic fields can significantly affect beam stability. They reference previous studies that have investigated the impact of wake fields on beam dynamics and stability. Overall, the authors' discussion of previous work on impedance modeling in single-bunch collective instability simulations serves as a foundation for their own research, which aims to develop a more comprehensive understanding of these phenomena in high-energy particle accelerators.